What exactly is time? It's one of the deepest questions that humans have ever asked. One of the leading theories is that time isn't real at all. It's just a construct of our brains. And we experience it because our brains are really complex computers which have evolved over millions of years to measure change. So let me ask you this. If you were dropped onto this beach one day and found this glass bottle, would you ever guess that inside this bottle is a portal to another dimension? Probably not. You'd probably think that this was just an ordinary bottle. But what if I told you that there was a different way of looking at things? What if I told you that actually this bottle is a portal to another dimension that has its own laws of physics? Well, in that case, maybe you'd start to think again. Maybe you'd take the lid off the bottle, lean in for a quick sniff, and then pop the cork. Whoa, time travelers. I bet you thought this was going to be a boring episode, didn't you? Sorry to disappoint, but here's the deal. Sometimes to understand the extraordinary, we need to approach it through the ordinary. So don't worry, we're going somewhere amazing today. We're going to outer space. We're going to black holes. We're going to learn some deep truths about time along the way. Let's go. Perhaps the most familiar thing in the universe, and yet the least understood. Every second, every heartbeat, every sunrise, every death all unfold within its flow. It defines our lives so completely that we rarely stop to ask the most basic question. What exactly is time? Is time a fundamental property of the universe, existing on its own? Or is it simply a human invention, a way of measuring change? The deeper we look, the more slippery it becomes. For centuries, philosophers imagined time as an eternal backdrop, infinite, absolute, and unchanging. But with the rise of modern physics, that picture was shattered. Time, we discovered, is woven into the fabric of the cosmos itself. Bends, stretches, and in extreme conditions, it may even stop. This episode explores time not as a ticking clock, but as a mysterious dimension of the universe. We will travel from the birth of time in the Big Bang to black holes, where time slows almost to a halt. We LSL ask why time seems to have a direction, why we can remember the past but never the future. And we'll explore what the ultimate fate of time might be as the universe drifts toward its end. Now, as you know, the universe began with the Big Bang. Before that moment, our universe did not exist. Nothing existed. There was no space, no time, no matter, no energy, no laws of nature. Then suddenly, space-time exploded into existence, and with it, the fundamental forces that govern our physical reality. Since then, the universe has expanded over 13 billion times, giving rise to stars and galaxies, black holes and quasars, and yes, life itself. And throughout this cosmic journey, time has been the constant companion, marking the passage of events that shape the cosmos. At the beginning, time was intimately linked with space. They were intertwined in a four-dimensional fabric called spacetime. Spacetime isn't just a passive background. It's a dynamic entity that responds to mass and energy. And time, well, it's one of the dimensions along this fabric. As light streams from distant stars, it takes time to reach us, much like ripples spreading across the surface of a pond. When we observe those stars, we're seeing them as they were in the past. The light carries information from long ago, and by observing it, we're peering back in time. If only we could see light from faraway galaxies without this delay, we would witness the universe as it truly is right now. But as we gaze at the cosmos, we're always looking backward. Even the nearest star is a year away, and the most distant ones are unimaginably farther. The vastness of space makes this delay significant. For instance, when you see a supernova in a faraway galaxy, you're not witnessing it in real time. You're seeing the death of a star as it occurred thousands or even millions of years ago. The light from these ancient events has finally reached our telescopes, allowing us to see them now. In essence, the act of observing these distant events transports us back in time. We become observers of the past, understanding the universe as it was in moments long gone. But there's more to it than that. Time, it seems, isn't just a tick-tock on the clock. It's a cosmic dance. A reminder that the universe never ceases to amaze. Now, do you feel like you've learned something new today? You have a newfound appreciation for the complexities of time? The story of time begins 13.8 billion years ago. And for that story to make any sense at all, we need to go back to the beginning. But be careful. Going back to the beginning might leave your head in a very strange place. Before the Big Bang, we cannot speak of before at all, because time as we know it did not exist. The Big Bang was not simply an explosion of matter into space, which the creation of space and time themselves. To understand this, let's take a step back from cosmology and consider a bouncing ball. In everyday life, the path of that ball seems simple enough. It goes up, it comes down. But if you were to plot that path on a graph, you would see that it is a smooth curve. That curve is a visual representation of the ball's position in space over time. Now imagine that same ball being thrown on a trampoline. Its path up and down becomes more complex, oscillating with the rhythm of the spring. If you plotted that movement, you wouldn't get a simple curve, but a series of loops. Each loop represents a single oscillation of the ball on the trampoline. But what if you took a closer look at these loops? You might notice that each one is distorted, stretched, and squashed in different places. If you examine the peak of one loop and trace it back to its matching point on the next, you'll find that the distance between them isn't the same. You might think you're just seeing an artifact of the way the graph is drawn, but it's actually something much more profound. Space and time are not absolute. They change depending on where you are. That change is represented by the distortion in the loops. The trampoline analogy illustrates a central concept in Einstein's theory of general relativity. Space and time intertwine in a four-dimensional fabric known as spacetime. And that fabric is not static, but dynamic, shaped and reshaped by the matter and energy contained within it. Spacetime tells matter how to move, and in turn, the matter moves spacetime. This interdependence means that asking what happened before the Big Bang is, in a sense, meaningless, because before implies a temporal framework. If time emerged at the Big Bang, then there was no before, only the timeless state from which our cosmos began. Let's rewind the clock, or rather imagine a clock that ticks backward. At the Big Bang, our universe was a singularity, a point of infinite density and temperature. There was no space, no time, only a potential for the universe that we know. Then came the Big Bang itself, a sudden expansion that catapulted the universe into existence. In the blink of a quantum eye, the universe was already a split second old. At this unimaginably brief instant, y-43 seconds after the Big Bang, the known laws of physics break down. Gravity, quantum mechanics, and relativity collide in ways that our equations cannot yet reconcile. We are at the Planck epoch, named after the German physicist Max Planck, who first proposed its existence. In this primordial instant, time itself may have been uncertain, not flowing as we experience it, but flickering in probabilistic fits. Our current understanding of physics suggests that at the Planck epoch, time was not a reliable metronome keeping steady beat. Instead, it was a jumbled drum solo, a cacophony of rhythms until the universe expanded enough for the fundamental forces to separate and for a semblance of order to emerge. As the universe expanded and cooled, something profound happened. Time became stable. The fundamental forces of nature split apart. Gravity separated from the other forces in a flash of light. The other forces then combined in a symphony of symmetry breaking to create the strong and weak nuclear forces and the electromagnetic force. Fundamental particles, the protons, neutrons, and electrons that form the building blocks of matter, condensed out of the energy sea. Atomic nuclei formed, and the first atoms, mostly hydrogen with a smattering of helium, appeared. With the advent of stable atoms, the stage was set for stars to ignite and galaxies to form. Time was no longer a jumbled drum solo. It became the steady beat of a metronome, reliable and consistent. The arrow of time, pointing from past to future, emerged with the universe's expansion and the rise of entropy, the gradual increase of disorder. Galaxies spun into existence, each a swirling island of creation nestled within the vast expanse of the cosmos. Stars ignited, marking their territories with the light of thermonuclear fusion. Planets coalesced from swirling disks of dust, some graced by the warmth of orbiting suns, others cast into eternal darkness. And on at least one small world, life arose, a testament to the universe's creative power. All of this unfolded under the watchful eye of a metronome whose steady beat kept time, measured out the universe's history, and ensured that the grand cosmic drama played out in its majestic progression. But remember, this metronome is not a constant. It's a product of the universe's structure, tied to the expansion of the cosmos, the interactions of particles, and the geometry of spacetime itself. And as we've seen, that structure is not static. Space and time intertwined in spacetime can stretch and distort, and they do so in ways that challenge our intuition about the constancy of time. This warping of spacetime doesn't just affect distant galaxies or exotic phenomena like black holes. It touches upon the very essence of time itself. Consider again the trampoline and the bouncing ball. The ball's path is altered not just by the trampoline's springs, but by the gravitational pull of the Earth. In fact, every object with mass warps spacetime around it, and that warping affects not just the paths of other objects, but the passage of time. The deeper the gravitational well, the slower time passes. This means that time runs faster on the surface of the Earth than it does near a black hole. And it also means that time is not the same for everyone. If you were to synchronize your watch with someone else's on Earth, and then one of you were to venture close to a black hole, while the other remained on Earth, eventually your two watches would diverge, showing different times. It's not just a difference in location, it's a difference in how time itself is being measured. This strange warping of time brings us to another dramatic demonstration of time's strangeness. Imagine a spaceship equipped with an atomic clock, the most precise timekeeping device known to science. If this spaceship were to approach the speed of light, something astonishing would happen. The clock would slow down. Time, for all practical purposes, would stand still for the astronaut on the spaceship. This phenomenon, known as time dilation, arises from the very nature of space and time intertwined in relativity. The faster an object moves through space, the slower it moves through time. At the speed of light, time effectively stops. This is not a mere theory. It has been experimentally verified. In the late 1970s, experiments using high-precision atomic clocks on jets confirmed that time passed slightly slower for the jet-setting clocks compared to those staying put. And it's not just hypothetical spaceships moving close to the speed of light. Even here on Earth, time is affected by relative motion. Take, for instance, the GPS satellites. These satellites orbit the Earth at high speeds and altitudes, and their clocks are affected by both their speed and their gravitational potential. As a result, they experience time slightly differently than we do here on the surface. If these time differences were not accounted for, the errors in positioning could be catastrophic. Thus, satellites rely on atomic clocks that are not only precise, but synchronized with Earth-based clocks. This synchronization takes into account the effects of both special and general relativity. In essence, GPS relies on an intricate understanding of how time is warped and stretched in different parts of the universe. So remember, time is not a universal constant, but a property of the universe's structure. It is tied to the expansion of the cosmos, the interactions of particles, and the geometry of spacetime itself. It can pass at different rates depending on where you are and how you move. From the tiniest quantum fluctuations to the grand sweep of galactic evolution, time is a dynamic player in the cosmic drama. Yet despite its elusiveness, its changeability, its dependence on the observer, we find ourselves inexorably tied to it. Whether we measure it with atomic clocks or the phases of the moon, we are swept along by its ceaseless flow. Time, in its relentless march, reminds us of our place in the grand tapestry of the cosmos, ever-changing, ever-moving, forever entwined in the grand dance of the universe. From the tiniest subatomic particles to the largest astronomical objects, everything in the universe seems to be governed by the same physical laws. But when Einstein proposed his theory of relativity in the early 20th century, it turned that around. One of the key pillars of relativity is that the laws of physics are the same everywhere in the universe. But they work in different ways, depending on your frame of reference. Take, for example, the speed of light. No matter where you are in the universe, if you measure a beam of light, no matter how fast you're moving, you'll always find it traveling at 300,000 kilometers per second. Or consider a simple swing. If you're sitting on a swing and someone pushes you, you feel a force pushing you forward. If you were to measure that force, it would have a particular value. But if that person who pushed you happened to be standing next to a black hole, the force of that push would be less than what you experienced. You would unnotice it unless you were a superpowered being able to measure that tiny difference in force. But from the perspective of someone far away from the black hole, the swing in question would appear to be moving so slowly that you would barely move at all. So when Einstein proposed that space and time intertwined in a four-dimensional fabric could be warped by mass and motion, it overturned our intuitive understanding of reality. Time, after all, was supposed to be universal, ticking steadily everywhere. Yet today, a century later, we don't just believe relativity, we rely on it. Two of the most dramatic demonstrations of relativity's grip on time come from opposite ends of human experience: the monstrous gravity wells of black holes and the tiny satellites orbiting Earth that guide us through everyday streets. Black holes. Time's abyss. To truly understand black holes, we need to rethink time. Black holes are perhaps the ultimate test of time's flexibility. These cosmic monsters form when massive stars collapse under their own gravity, squeezing matter into a region so dense that not even light can escape. The boundary around a black hole, called the event horizon, is a one-way frontier. Anything crossing it is lost forever. But the strangest thing about black holes is not what they consume, it's what they do to time. According to general relativity, gravity is the warping of space-time by mass. The stronger the gravity, the more space-time curves. Near a black hole, space-time curves so severely that time itself slows down relative to regions farther away. Imagine an astronaut orbiting just outside the event horizon. To her, time seems normal. Her heart beats steadily. Her watch ticks as usual. But to a distant observer, her clock appears to run slower and slower the closer she drifts toward the horizon. From their perspective, she never quite falls and her time appears to freeze at the edge. This phenomenon, called gravitational time dilation, means that time is not absolute, can stretch and warp depending on the strength of gravity. In the vicinity of a black hole, this effect is extreme. Hours for the astronaut might equal centuries in the wider universe. This concept was famously illustrated in the film Interstellar, where astronauts visiting a planet near a supermassive black hole experience minutes, while years pass outside. While dramatized, the science is real gravity can turn time into something almost unrecognizable. Black holes are not only astrophysical curiosities, they are laboratories for time itself. At their hearts lies a mystery. If time slows infinitely at the event horizon, what does it mean inside? General relativity predicts a singularity, a point of infinite density where our laws of physics collapse. Some physicists argue that at this point, time itself may end. GPS satellites. Time travelers aboard modern technology turns on Einstein. GPS satellites silently circle the Earth, making time travel possible. Well, not exactly. You won't find them on any time traveler's map, but they do prove Einstein's theories in action. The Global Positioning System works by using a network of satellites orbiting about 20,000 kilometers above Earth. Each satellite carries atomic clocks, which send precise timing signals to the surface. Your GPS receiver calculates how long those signals take to reach you. Using that information, it pinpoints your position on the globe with meter-level accuracy. But there's a complication. The clocks on those satellites do not tick at the same rate as clocks on Earth. Two effects come into play. First, special relativity says that because the satellites are moving quickly relative to Earth's surface, their clocks should run slower. Second, general relativity says that because they are farther from Earth's gravity, their clocks should run faster. The upshot, satellite clocks tick about 38 microseconds faster per day than clocks on Earth. That might sound tiny, but without correction. GPS would accumulate errors of about 10 kilometers every day, making the system useless. To make GPS accurate, engineers must factor in Einstein's relativity equations. In other words, your smartphone works because of the strange, counterintuitive nature of time itself. Both these examples show how time is not a constant in our universe. It is shaped by the very forces that define it, and that raises another question. If time can bend and shift in different circumstances, then why does it always seem to flow in the same direction? Why does it always flow from past to future? Even this question has its own surprising answers. As we dig deeper into the mysteries of time, we find ourselves questioning the very nature of reality. What seems intuitive and obvious is often just a starting point for a journey into the unknown. Time, despite being omnipresent, is notoriously difficult to define. How many seconds are in a year? What was the time before the Big Bang? And how will we measure time when the universe reaches heat death? Please. Are perplexing questions, but they are not the ones that concern us here. When we think about time, it seems so straightforward, yet so strange. Looking back over our lives, we move from birth to childhood, to adulthood, to old age. Life changes. People come and go. Planets orbit, stars, seasons turn. But when we examine time closely, everything becomes much more complicated. For starters, time feels like it's passing. Yet if we look at the universe in detail, it appears fundamentally static. Nothing ever jumps backwards. A broken vase never unbreaks. People do not unmeet. Eggs do not uncrack. Cats cannot unkill. Right. Time moves only forwards. So why is the world dynamically asymmetric, when every physical law we know is perfectly symmetrical? Why do we only seem to move from cause to effect, never from effect to cause? This is the problem of the arrow of time. Most physicists believe the origin of the arrow of time lies in thermodynamics, which studies how energy behaves in complex systems. Consider a cup of coffee. At first it is hot, meaning its molecules move around quickly. But over time, those molecules bump into the air molecules, and they transfer energy until the coffee is at room temperature. As the coffee cools, entropy wins. A second law of thermodynamics tells us that entropy always increases in a closed system. In a closed system, any small amount of order spontaneously evolves into a larger amount of disorder. This tendency for things to spread out and decay is the driving force behind the apparent motion of time. Because of this, we remember the past, but not the future. We go forward from a hot cup of coffee to a cold cup of coffee, but never the reverse. It all boils down to probability. The number of ways a hot cup of coffee can get colder is vastly greater than the number of ways it can spontaneously get hotter. If we were to reverse time, we would see hot coffee unspontaneously get hotter, which is extremely unlikely. For example, if you scrambled an egg, it wouldn't unscramble on its own. You need to put energy into it to unscramble it. In the same way, we can't reverse time, because that would require a highly unlikely event to happen. Of course, we could just postulate that there are other forces that would prevent the world from getting too disordered, such as dark energy. But then, we would still need to explain why the universe started off so ordered in the first place. For example, why were the protons and neutrons in such perfect balance at the start of the universe, that after expansion they could form such perfect nuclei of helium? Why is the cosmological constant so finely tuned with respect to the matter density of the universe? If we ignore dark energy and dark matter, these two constants would have to be 120 orders of magnitude apart to get a viable universe. But with dark energy included, their ratio is only 120. Problem solved. Well, kind of. The issue is that the anthropic fine-tuning argument begs the question of how life came to be. Maybe life only arose in universes that satisfied the criteria for life to arise. But then we would still need to explain why time moved forwards in that particular universe. So the mystery persists. The strange properties of time are made even stranger when we bring Einstein's theories of special and general relativity into the mix. The foundations of both these theories rest on the idea that time must be treated alongside three dimensions of space as part of a four-dimensional continuum called spacetime. According to this view, all points in space and time are equally real. However, as we saw earlier, the passage of time implies an asymmetry between past and future. To reconcile these ideas, we use the concept of simultaneity. This is the idea that an event happening at one place in space might not be simultaneous with an event happening elsewhere, but could be simultaneous with an event happening in the past or future at another location. Simultaneity allows us to say that there is no absolute now. Whether or not two events occur at the same time depends on your frame of reference. This means that if you were to map out the entire history of the universe, the past, present, and future would all exist at once. This is the block universe. This might sound counterintuitive, but it's mathematically elegant. In fact, the block universe is a cornerstone of Einstein's general relativity. In general relativity, all moments in time are equally real, and there is no objective distinction between past and future. That this raises several questions. If the future is real, does that mean that we can never truly be free? Since our decisions today will inevitably lead to specific outcomes tomorrow, this conclusion seems unavoidable. But surely there must be some way to resolve this paradox. One idea is that the block universe is nothing more than an artifact of mathematics. While it's undeniably useful, it doesn't tell us anything about the underlying physical reality. In that case, there must be something deeper going on. A deeper layer of reality, according to some, contains no time at all. In this view, the universe is timeless. Sounds crazy, right? Well, hear me out. Some physicists have found ways to reformulate Einstein's general relativity without using time. In these reformulations, the fundamental equations of physics apply only to the present moment. While the idea of a timeless universe might be hard to wrap your mind around, it is mathematically elegant. Unfortunately, there are problems. For example, if time is not fundamental, what causes the observed flow of time? Or worse, if the laws of physics contain no time, why do we experience time passing? The honest answer is that nobody knows. There are lots of interesting candidates, but unfortunately, none are good enough to have gained widespread acceptance among physicists. The search for a fundamental theory of time is one of the biggest open problems in science. What are we to make of all this? First, we should take comfort in the fact that we do need a fundamental theory of time to understand how to make an omelet. Our everyday intuitions about time are good enough for most purposes. But it is natural to want to understand the deeper implications of our experiences. What is the source of the arrow of time? Why do we experience time passing? And if time is emergent, what is it emergent from? These are deep questions. While we do not have definitive answers, we do have frameworks that allow us to ask deeper and deeper questions and make sharper and sharper predictions. And as long as humans exist, the search for answers will continue. As Carl Sagan once said, we live in a magnificent universe, a universe of atoms, a universe of molecules, a universe of cells, a universe of life. But what drove you to start searching for those answers in the first place? Was it a calling, an itch that needed scratching, a bet you had to win? Whatever the reason, it was probably worth it. After all, thanks to your curiosity, we've been able to learn more about the nature of our existence than any other creature in the universe. How did we conquer time? It's one of the questions I explored in my book Cosmos in a minute. Here's an excerpt. From the dawn of humanity, we have pondered the nature of time. Is it an eternal, unchanging reality, or a human construct? As we contemplate this profound question, we are led to believe that time is a universal constant. However, recent scientific discoveries have revealed that time might not be as straightforward as we once thought. Einstein revolutionized our understanding of time by demonstrating that it is intertwined with space, forming a four-dimensional continuum known as spacetime. He showed that time is not absolute, but rather relative to the observer's frame of reference. This means that time can be affected by factors such as gravity and velocity, leading to different experiences of time in different locations. Imagine two observers, one near a massive black hole and the other far away in deep space. Due to the intense gravity near the black hole, time would appear to pass more slowly for the observer near it compared to the observer in deep space. Additionally, if an object were to travel at a significant fraction of the speed of light, time would also pass more slowly for that object relative to a stationary observer. These mind-bending concepts challenge our intuitive understanding of time and highlight its interconnectedness with the other dimensions of space. However, these ideas raise new questions about the fundamental nature of time. For example, what is the role of time in the quantum realm? Does time behave differently at the atomic and subatomic levels? To understand the behavior of time in the quantum realm, we must delve into the realm of quantum mechanics. Quantum mechanics is a branch of physics that studies the behavior of matter and energy at the atomic and subatomic levels. It has revealed a world where particles can exist in multiple states simultaneously and where the act of observation affects the outcome of experiments. When we apply the principles of quantum mechanics to time, we encounter some truly bizarre phenomena. One such phenomenon is time symmetry. According to the laws of classical mechanics, time is said to be reversible. This means that if we were to reverse the direction of time, the motion of objects would simply play out in reverse. However, at the quantum level, time appears to be more like a movie playing on a loop. It runs forward and backward with equal likelihood. This symmetry suggests that time itself is not a fundamental property of the universe, but rather an emergent phenomenon, arising from more fundamental underlying principles. Another puzzling aspect of time in the quantum realm is the problem of time. This problem arises because, in quantum mechanics, time is treated as a parameter rather than a dynamic variable. This means that time is assumed to be fixed and flowing in only one direction. However, this raises the question of why time flows in only one direction, when the laws of quantum mechanics are time-symmetric. Resolving this apparent contradiction has been a major challenge for physicists, and has led to various interpretations of quantum mechanics. One interpretation is that time is an illusion, and that the universe exists outside of time altogether. This idea aligns with some mystical and spiritual beliefs, but it remains highly controversial within the scientific community. To further unravel the mysteries of time, we must turn to cosmology, the study of the origin, evolution, and structure of the universe. Cosmological observations have provided us with an unprecedented understanding of time on the grandest scales. By observing the behavior of galaxies, stars, and other celestial objects, cosmologists have been able to piece together the history of the universe and make predictions about its future. One of the most significant discoveries in cosmology is the concept of the Big Bang. The Big Bang theory is the prevailing cosmological model for the universe. It describes the universe as having originated from an extremely hot, dense state approximately 13.8 billion years ago, and then expanding and cooling over time. This theory is supported by a wealth of observational evidence, including the redshift of distant galaxies, the cosmic microwave background radiation, and the abundance of light elements. Moreover, observations of distant galaxies have revealed that the expansion of the universe is accelerating. This discovery has led to the introduction of dark energy, a hypothetical form of energy that is thought to permeate all of space and is responsible for this accelerated expansion. Dark energy has been proposed as a possible solution to the problem of time in cosmology. If time is not a fundamental property of the universe, but rather an emergent phenomenon, then dark energy could be the driving force behind the apparent flow of time. However, the exact nature of dark energy remains unknown, and its relationship to time is still highly speculative. As we continue to explore the mysteries of time, we must also consider the philosophical implications of our findings. The realization that time is not absolute but relative challenges our intuitive notions of reality. If time is not a universal constant, then how do we define the present? And if time is not linear but cyclical, does it mean that the future is predetermined? These questions have profound implications for our understanding of free will, determinism, and the nature of existence itself. In conclusion, our understanding of time has undergone a radical transformation in the past century. Einstein's theories of special and general relativity revolutionized our conception of time by showing that it is intertwined with space and relative to the observer's frame of reference. Quantum mechanics has revealed the bizarre properties of time in the subatomic realm, such as time symmetry and the problem of time. Cosmological observations have provided insights into the evolution of the universe over billions of years and have led to the development of models such as the Big Bang theory. As we continue to probe the depths of time, we must also confront the profound philosophical questions it raises about the nature of reality, free will, and the very essence of existence. The more we learn about time, the more we realize how much there is still to discover. The quest to understand time is a testament to the boundless curiosity and ingenuity of the human spirit. Each new discovery brings us closer to unraveling the mysteries of the cosmos and our place within it. Whether we are contemplating the vast expanses of space or the intricacies of subatomic particles, our journey to understand time reminds us of the interconnectedness of all things and the profound beauty of the universe we inhabit. As we reflect on the profound mysteries of time, let us also celebrate the remarkable achievements of those who have dedicated their lives to unraveling its secrets. From ancient astronomers who first mapped the celestial sphere to modern-day physicists who probed the depths of the quantum realm, each generation has contributed to our growing understanding of time. From the dawn of humanity, we've been fascinated by time. Some say it's the most precious commodity. Others claim it's an illusion. So how do we get from the tick-tock of the clock to the endless tick-tock of the cosmic clock? Time is the dimension in which things change. It's the river in which events flow. You might think of time as the third dimension. That's because every point in space has a pair of coordinates, like latitude and longitude, or x and y. But these tell us nothing about when something happens. To pinpoint a moment, we add a third number, time, t, like 3:15 p.m., to specify a precise instant. If we add another spatial dimension, we get 4 coordinates, enough to chart everything that happens in our everyday world. But this still isn't enough to chart the entirety of our reality. We need to add another time dimension, giving us 5 dimensions total. And if we remove our location from the time stream, we get the equivalent of 4-dimensional space. It's hard to imagine these extra dimensions, but they're critical for our existence. Without them, the universe couldn't work. Newtonian time started out as a philosophical idea. In the 17th century, most Europeans believed time and space were infinite. They thought the universe had no beginning and no end. But then came Nicolaus Copernicus, who placed the sun at the center of the solar system and set the Earth spinning on its axis. Now people saw the Earth speeding around the sun, falling around a curved path through space. If the sun could escape the bonds of space, where would it go? How could it keep falling? Enter Galileo Galilei, who asked, if time and space are infinite, why doesn't the sun fall off the edge? He calculated that infinite space and infinite time aren't physically possible. There has to be a limit. And in 1687, Isaac Newton published the laws of motion and universal gravitation. He showed that planetary orbits and projectiles follow predictable paths in space based on force and mass. Newton combined this with his 3 laws of motion, creating a framework that could explain how the universe worked. His book, Philosophy, Naturalis Principia Mathematica, established the foundations of classical mechanics. It contained what would become the dominant view of time for the next 200 years. Time, he declared, was absolute, universal, and unchanging. Absolute in the sense that it was the same everywhere and belonged to the same system for everyone. Universal because it applied to everything and never changed. This absolute time gave the universe structure and predictability. It made clear what went before, what was happening now, and what would happen next. But even Newton knew that time wasn't everything. He proposed a distinction between what we call time and duration. Duration, according to Newton, is the length of an interval between 2 events. For example, the duration of your life is the length of time between when you were born and when you die. But time isn't the same thing as duration. Time is the ongoing flow. It's all the moments in succession. Think of it like a river. The river flows continuously, and each drop of water represents a moment in time. The duration of the river is the length of time it takes for a particular drop of water to travel from the source to the sea. But the river keeps flowing, endlessly creating new drops of water, new moments in time. Newton thought that this flow of time was created by God. It was an act of divine creation that allowed the universe to exist. This is why he called it absolute. It was independent of the universe and had no beginning or end. It simply existed, flowing eternally, allowing the universe to unfold as it should. Einstein turned that around. In 1905, he revolutionized our understanding of the universe. He proved that the speed of light is constant for all observers, no matter how fast they're moving. This is known as the second postulate of special relativity. The first is that all physical laws are the same in all non-accelerating reference frames. These postulates led Einstein to conclude that space and time cannot be separate. He showed that they were intertwined in a 4-dimensional continuum called spacetime. Spacetime is like a fabric. When something massive is placed on it, it causes the fabric to sag or curve. In 1915, Einstein developed his general theory of relativity, which showed that gravity is a result of this curvature in spacetime. Gravity isn't a force, but a consequence of objects rolling toward each other along the curves of spacetime. Since then, physicists have known that the relationship between space and time is more complicated than Newton imagined. Time isn't just an external backdrop, it's a player on the field. It's affected by gravity, velocity, and the very matter it's intertwined with. Remember that time is the third dimension. If we removed our location from the time stream, we'd see only 4-dimensional space. It means we can use the language of space to describe changes in time. In the case of a black hole, we say that time stops at the event horizon, the point of no return. But really what happens is that time slows down until it reaches zero at the horizon. This means that inside a black hole, time runs backward. So if you wanted to reverse the flow of time, you'd need to enter a black hole. Physicists have continued to refine our understanding of time ever since. In the mid-20th century, they discovered that space-time can be quantized, meaning that it can exhibit properties of both waves and particles. Waves like light spread out over space, while particles like electrons are localized. But when physicists tried to apply quantum mechanics to space-time, they ran into a problem. They found that the fabric of space-time seemed to be smoother than the surface of a piece of paper. That's because the smallest possible length is zero. So any length greater than zero is infinitely large compared to it. This is known as the Planck problem. It says that quantum effects become negligible at distances larger than the Planck length, which is about 10 to the minus 33 centimeters. This is important because it tells us that quantum mechanics is irrelevant on the scale of galaxies and stars, but it becomes crucial on the scale of subatomic particles. Fortunately, we do know how to combine the quantum properties of small things with the relativistic properties of big things. The hope is that when we figure it out, it will solve the problem of time. But meanwhile, scientists have been busy pushing back the frontiers of time in other ways. They've measured the age of the universe, which is about 13.8 billion years old. And they've explored the conditions that existed before the Big Bang. According to current theories, the universe had a beginning, a hot, dense state known as a singularity. But what happened before that? Was there a time before time? Some physicists believe the universe is cyclical, oscillating between periods of expansion and contraction. Others believe it's eternal, having existed forever in a state of constant flux. With the discovery of dark energy, which is accelerating the expansion of the universe, the question of the heat death of the universe has become increasingly urgent. Dark energy is a mysterious force that seems to be causing the expansion of the universe to speed up. The effect is strange and unexpected, and scientists are still working to understand it. But it has profound implications for the fate of the universe. Dark energy is the dominant force in the universe today, making up around 68% of its total mass and energy budget. It's a repulsive force that acts over vast distances, pushing galaxies away from each other and driving the accelerated expansion of the universe. Its discovery in the late 1990s was a shock to the scientific community. At the time, most astronomers expected that the expansion of the universe was slowing down under the influence of gravity, but instead they found that it was speeding up. This unexpected observation led to the hypothesis of dark energy as a possible explanation. In the distant future, as the universe continues to expand, the effect of dark energy will become even more pronounced. Most physicists believe that the heat death of the universe will occur when the expansion of the universe overwhelms all other forces, completely dispersing all matter and energy. At this point, the universe will reach a state of maximum entropy, and no further changes will be possible. As the universe expands, stars will die out, leaving only remnants like white dwarfs, neutron stars, and black holes. Galaxies will drift apart, and the night sky will become dark and empty. Even the atoms that make up planets and other solid objects will eventually break down, due to the combined effect of dark energy and the heat death of stars. This is a bleak future, but it's not necessarily the only one. Some physicists speculate that the universe could collapse in on itself and begin again in a new cycle of expansion. Others believe that the universe could split into multiple parallel universes, each evolving independently of the others. These ideas are highly speculative, and there's currently no evidence to support them, but they offer intriguing possibilities for the future of our universe. Today, physicists are probing time in new ways. They're searching for evidence of quantum gravity, which is the force that brings the very large and the very small together. They're also looking for signs of dark energy, the mysterious force that's accelerating the expansion of the universe. And they're exploring the nature of black holes, which are regions of space-time where gravity is so strong that nothing, not even light, can escape. Each of these areas of research offers a unique window into the nature of time and its role in the universe. By studying them, physicists hope to shed new light on some of the most fundamental questions in cosmology. Time has long captivated human thought. From the ancient Greek philosophers to the modern physicists, we've been fascinated by its nature and its role in the universe. Newton saw it as an absolute and unchanging backdrop to cosmic drama. Einstein revealed its intertwined relationship with space and its dependence on gravity and motion. Today, we're pushing the boundaries of our understanding of time, exploring its behavior at the extremes of the very large and the very small. Whether it's the eternal stage of Newton's universe or the ever-shifting landscape of Einstein's relativity, time remains one of the most profound mysteries and challenges of our existence. There's a scene in the 2014 movie Interstellar where the protagonist, played by Matthew McConaughey, is trapped in a near-infinite loop. He finds himself repeatedly reliving the same few minutes aboard a spaceship orbiting a black hole. Every time he tries to break free of the loop, every time he tries to move forward, he's pulled back again and again and again. Now, this concept can be a bit confusing. What's the point of time if it's constantly repeating itself? Does time have a purpose? How does it work? Well, it turns out that in real life, we also find ourselves in a similar situation. We keep reliving the same period of time over and over again. Just like Cooper in Interstellar, we don't know how to get out of this loop or what to do about it. We're living in an era of scientific stagnation. We don't know what happened before the Big Bang, which makes sense because up until the late 19th century, people didn't know what a photon was or how stars worked. And right now, we don't know what comes after the heat death of the universe, and that's a problem. You see, we like to think of time as endless, an infinite backdrop against which the drama of the universe plays itself out. But that's probably wrong. Our universe has a history. So too might time itself. And just like we can use the behavior of the universe to infer something about the nature of time, we can use the fate of the universe to try to figure out what happens to time. What happens when the universe reaches its end? This question is one of the deepest in science and philosophy. What happens to time when the universe dies? Welcome to my channel. If you want to better understand the world around you and the universe within reach, subscribe for more videos like this one. So there are two things to keep in mind here. First, time doesn't actually exist. It's not a physical thing that's measurable, like space, mass, or electric charge. Rather, time is best understood as a way of describing change. Consider that everything we say about the passage of time is really a statement about something else changing. When I say 1 minute passed, what I really mean is that 60 seconds elapsed between two moments. And when we talk about the future or the past, we're referring to events that happened either after or before other events. Time is intimately tied to change, and it goes hand in hand with entropy, which is the tendency of things to become more disordered. And this brings me to the second thing we need to keep in mind, which is that we're living in a universe that started with a bang, meaning everything began in an extremely orderly state. For example, all of the hydrogen and helium in the universe is found in extremely dense blobs called halos, and those blobs were spinning around in perfect circles. If you were to wind the film back and watch the universe start over, it would be like rewinding a movie to the point where there's a tennis ball suspended in midair above the court just before someone hits it. That is, all of the motion is perfectly still. Such a state of affairs is highly unlikely to occur naturally. And according to our best estimates, it's virtually impossible that this would have happened by chance. Instead, scientists believe that the universe was created in a state of low entropy, because there was an agent at work actively organizing the primordial stuff. What scientists refer to as the anthropic principle basically says that because we are here, we know that the universe started out in a special way. It needed to start out in a very orderly state in order for life to emerge and evolve. So the inevitable fate of the universe is to return to disorder. Everything will eventually settle into its most likely state, which is one of uniform distribution. To put it simply, everything will eventually become evenly distributed. The question is, how will this happen? What will the universe look like when it reaches the end of its life? Well, there are lots of different ways to answer this question, but two of them stand out as particularly compelling. The first is the heat death of the universe. According to this scenario, which is by far the most popular among astronomers and physicists, entropy continues its relentless rise, until all the usable energy in the universe is spread thin. Stars burn out, galaxies drift apart, and even black holes, which have the strongest gravity in the universe, will eventually evaporate through a process known as Hawking radiation. Eventually, all of the matter in the universe will decay into subatomic particles, and those particles will decay into radiation. All of these things will eventually come into thermal equilibrium, which means that the entire cosmos will be filled with a thin mist of low-energy photons that are evenly distributed. The only evidence of what once existed in this cold, dead universe will be the faint afterglow of creation and the echoes of light from long-dead stars. Space will be filled with ghosts of light. The key characteristic of this universe is uniformity. There will be nothing anywhere except evenly distributed, low-energy photons. In such a universe, time loses its meaning. Without change, without processes, without clocks to tick, the flow of time becomes indistinguishable from stillness. The arrow of time, which depends on increasing entropy, may vanish entirely. Time, in this view, fades into silence as the cosmos reaches its maximum disorder. Another possibility arises if dark energy grows stronger over time. Dark energy is the name given to the force that is causing the expansion of the universe to speed up. According to this view, the expansion doesn't just continue, it accelerates without bound. Galaxies first drift apart, then solar systems, then planets, and eventually, even atoms themselves are torn apart by the runaway expansion. This is the Big Rip. If the Big Rip occurs, time might end in a catastrophic finale. As space-time stretches faster and faster, the very framework that allows clocks to tick is destroyed. Unlike the heat-death silent fade, the Big Rip represents a violent tearing of time's fabric. Now there are other possibilities too. Some cosmologists explore cyclic models where the universe undergoes repeated expansions and contractions. In such scenarios, time might reset with each cycle, giving rise to an eternal sequence of universes. For example, in the so-called conformal cyclic cosmology, our universe is just one bubble in a vast multiverse, and there are an infinite number of other universes, each containing an infinite number of other timelines. In that case, time never ends. It keeps going forever. However, these ideas are highly speculative and depend upon physics beyond the standard model, so I won't spend too much time talking about them here. Instead, let's focus on the first two scenarios. In a heat-death universe, time fades away to nothingness. It disappears because there is no longer anything happening. Nothing is changing, so there is no time. By contrast, in a Big Rip universe, time doesn't fade, it explodes. The Big Rip tears time to pieces, scattering it to the winds, along with everything else. So neither scenario is particularly satisfying. Both of them leave us with more questions than answers. For example, if time ends in the heat death, then why did it start in the first place? If time ends in the Big Rip, then what caused the Big Rip? Well, scientists don't have any good answers for those questions. In fact, those are some of the biggest unanswered questions in modern physics. However, both of these scenarios have a lot in common. In each of them, time ends because the universe reaches some sort of stable state. In a heat-death universe, the stable state is one of maximum entropy, while in a Big Rip universe, the stable state is one of maximum expansion. The universe becomes static. Either way, the universe becomes static. However, I want to pause here and point out that there's another possible interpretation of these scenarios. You see, if a theory of quantum gravity reveals that time isn't fundamental, then both heat death and the Big Rip might be only partial stories. The deeper reality could be timeless, with what we call time, emerging only within certain conditions. For example, the physicist Roger Penrose has suggested that time might emerge from quantum fluctuations in a deeper underlying reality. In that case, asking whether time ends might be like asking whether temperature ends when a cup of coffee cools. Temperature doesn't vanish from reality, but it ceases to exist meaningfully in that particular system. Instead, the heat flows from the hot coffee into the surroundings until it reaches a state of thermal equilibrium, at which point we say the temperature is the same as the surroundings. So in this view, time doesn't end. It just becomes meaningless. Of course, this is all highly speculative and controversial. But the main takeaway here is that the nature of time is intimately tied to the nature of our universe. If the universe has a beginning and an end, then so too might time. But if the universe is eternal, then time might be eternal as well. So that leads me to our final question, which is, what should we make of this? What does it mean for time to have a beginning and an end? And what does it mean for time to be eternal? Honestly, I don't know. It's probably best to think of time as a tool that we use to describe our experiences and interactions with the world around us. From the birth of a star to the death of a galaxy, from the beating of a heart to the cooling of a corpse, time serves as the metronome of existence. Even our memories are indexed by time, which provides a framework for the narrative of our lives. But while we may be able to understand the passage of time, we may never fully comprehend its essence. The true nature of time may lie beyond our perception, beyond our understanding. We can marvel at its patterns, trace its rhythms, and measure its intervals. But the deeper secrets of time may forever elude our grasp. Just as we can never see the wind, but only its effects, we may never know the true nature of time, but only its passage. Time shapes our existence, yet its own essence remains a mystery. All the stuff that I talked about in this episode can be really difficult to understand, but I'm here to help you through it. So feel free to ask questions. Thanks for watching. See you next time.